In this activity, we're going to implement P-only control or proportional-only control with the temperature control lab. P-only control is simplest control, and so it's easiest to tune. One side effect, though, is in non-integrating systems such as the temperature control lab, we may have persistent offset. We have the heater setting is going to equal the Q bias plus a constant Kc times the error, or the difference between our set point and where we are. You can see really quickly our tuning correlation, the ITAE tuning correlation for our Kc constant. We can look at a P-only offset simulator. Here we're going to simulate our temperature control lab. We're going to assume that Kp is equal to 0.9, tau p is equal to 1.75, and our dead time is 15 seconds. We can observe the offset as we change and manipulate Kc. You'll also notice that as we increase Kc, as we get more aggressive, we'll have more oscillation. You can notice that peak and those oscillations starting to occur. If we go all the way to 15 even, you can see there's quite a bit. Let's actually figure out what the best Kc, or at least the Kc with, let's say Kc ITAE is going to be equal to 0.2 divided by Kp, which is 0.9, times tau p, so 175.0 divided by 15.0, and all of that to the 1.22. So if we run this section again, it should be about 4.5. So if we set it at 4.5, that's what the ITA tuning gives us. And we'll see now how this simulation compares to our actual results. We have P-only control with TCLab. Our first objective is to determine the offset from a set point from 23 degrees to 60 degrees. So we're going to change our set point and look at how the controller responds. Previously what we've done is we've changed the heater setting and looked at how it responds. Now our objective is to change the set point and let it run for itself. You'll notice here, right here for the Kc, I plugged in this equation we had before, the ITAE equation. That's in that code block as well. Let's run through what this is going to do. First, it's going to attempt to read the matrix at absolute path. We've done this before. Next, if that doesn't work, we're going to create what Kc should be, and we're going to create our arrays. We have arrays for time, TM TCLab. T1 will record the temperature. Q1 will record the heater setting. E1 will record the error. And SP1 will record the set point at any given time. We'll then connect to the temperature control lab. We'll set Q1 bias to 0 and start our timer with tick. Then, for each time within the loop, we'll record the time, we'll record the temperature, we'll record the error as the difference in set point minus the temperature control lab temperature reading. And then our heater setting will be Q1 bias plus Kc times E1 at that given time. We'll then implement the new heater value, and here we're just making sure that the heater value is between 100 and 0. So we'll take the maximum of 0, so we'll start in the very center. We're taking the minimum of 100 and Q1. So the highest it can be is Q is 100. Then we're going to take the maximum of 0 and that number. That's maximum is 100. If it were negative, then it would turn out to be 0. Then we'll set the actual heater value to what we've just calculated. Then every 20 seconds we'll print out what actually is going on, just so that we can have a feel for what's going on. And then we'll wait for the remainder of that second. Finally, we'll save it in the matrix so that we can use it later if we need. So let's go ahead, let's run this section. And I'll see you on the flip side. Here we have our results graph. Let's go ahead and discuss what we can observe here. We have three graphs, one with the temperature and predicted temperature with our FOPDT model. The second is the heater value and the predicted value, and the third is our error. You'll notice on the temperature, there's a little bump with our the red dots in our temperature control lab data. That's actually because my air conditioning turned off right there, so we're able to reach a new average and we're able to reach a higher temperature. There's still some persistent offset between our set point of 60 and our actual measured values of, it looks like about 42 to about 50. We'll discuss how to overcome that offset in our next module with PI control. Next we have our heater values. You'll notice again that we have higher values than we expected in our FOPDT because our temperature is lower than we expected. And then we'll have our area. You'll notice that our area is consistently getting smaller and then reaches about a plateau. And that's kind of what we expect with a P-only controller. We reach a certain point where the proportion gives us a certain amount of heater action, and that heater action reaches steady state with the dynamics of the system. Like I said before, we'll look at how to eliminate that offset in the next module with PI control. Please let me know if you have any comments or questions. I'd be happy to answer them.